About the agenda of today. The main question of this webinar is how to correctly evaluate the feasibility of solar system. Or in other words, is solar power supply reliable? Because whenever we speak, we discuss solar airfield lighting systems with airport authorities, with consultants, with designers, with military users. They all have this essential question is, can we rely on solar power supply when we talk about airfield lighting? Is it redundant? Is it safe? Is it predictable? So in order to answer this question, here are three subtopics that we would like to cover today. Number one is how to assess reliability of solar power supply. We define reliability of power supply as a guarantee that system will operate continuously without any interruptions. Next subcategory is how to calculate risk of blackout in solar powered runway lighting. Well, blackout is defined as a inoperability of runway light, so no lighting due to temporary lack of power supply. And at the end, I will cover topic of are all solar powered systems equal? So we will talk a little bit about our competitors and the differences between S4GA and competitive systems. To start with, let me give you a few basic informations about S4GA. Number one, we are a state-owned company based in Poland, in the European Union. This is where all systems are manufactured, and this is where they are shipped from. We design, we supply the world's safest runway lighting, and entire portfolio of S4GA is certified in accordance with I'm sorry, ICAO and EASA requirements. If you look at this map of systems that we have delivered, first of all, so you need to understand that today S4GA is installed in more than 50 countries and in 125 different places. We installed our systems in countries that can be perceived as a not an optimal place for solar installation, such as Canada, or currently we are working on the project in Scotland. France, we delivered, Lithuania. So those locations are normally would not be perceived as a solar optimal, but they are, and I will explain why. And of course, we are strong in Africa, in Asia. We have several installations in Latin America as well. Today, we have delivered systems for civilians, for military, and we mostly focus on non-wired, in other words, wireless systems, non-conventional, solar-powered or portable systems. I'm talking about runway lighting systems and helipad lighting systems. Let me give you just few examples of solar-powered installations. This one in particular is the system is installed in Thessaloniki International Airport in Greece in 2017. This airport is managed by Fraport from Germany, a big airport operator. This particular airport required to close the main runway for rehabilitation, and they used a parallel taxiway as the primary runway for a few months. During this time, they have procured and installed S4GA solar-powered system, and they use it permanently for 6 or 8 months. We have supplied to them a solar system, solar lights, and a control system. Entire installation has been approved by Hellenic Airport Authority, which is a civil aviation authority of Greece. Another example, pretty typical for our installations, is one of the islands of Maldives. They have reclaimed the land and have built entire runway of category 3C which is around 1.8 kilometers long, and decided to go for solar lighting due to the fact that it is a sustainable solution, it is green and ecological, and also due to the fact that they have no reliable power supply on this island other than a single generator. So they decided to go solar and installed solar powered lights like this one here on runway, taxiway. We also installed a PAPI system that is also solar powered, and the taxiway that you can see right here. Entire system is controlled from the tower using radio network, and also it is monitored using the same network. Another again typical case for us, it's a remote airbase in the this one is in North Africa, system installed 2016. Customer wanted to equip one of the runways with a solar system. Why? Because entire airbase has been previously devastated. It was vandalized, and their conventional system that was previously installed there was not operational. So, and they also required to quickly illuminate the airbase for permanent usage. So we installed their solar powered lights, signs, wind direction indicator, and also a control system. What are the difference between solar and conventional system? Just to give you again, for some of you it's going to be just a refreshing information. For some of you maybe it's new, but I think it's important to understand. First of all, solar system that we as S4GA that we offer is world's safest runway lighting. Why we say that is because, well, first of all, it operates 365 days on solar. So operation of S4GA system cannot be interrupted by failure of the power supply, either mains or generator. The second aspect is that our system is equipped with 5-level protection against system failure. When we say system failure, we define it as complete and sudden, unexpected lack of lighting at the airport. We don't mean, and we don't refer to single light in-op or 2 lights or 3 lights. We mean that for us, system failure means no lights, emergency, airport has to abort flight operations immediately. So in case of S4GA system failure, total system failure is impossible due to the 5-level protection against it. In terms of control, entire system is controlled wirelessly, usually using so-called wireless mesh network, which means that when the signal is sent to any light of the system, then the signal is retransmitted from light to light because each light is a repeater. This way, range of radio operations is practically unlimited, because even if signal cannot reach from controller the most further located light, it will reach it through other lights. So non-directly via other lights, but it will reach it. And actually the propagation, the delivery of signal, even on the runway of 4 kilometers with few taxiways, takes not more than 1 second. On top of that, because each of light is individually powered and individually monitored, we offer our customers individual light monitoring of parameters such as battery level, solar efficiency. We calculate amount of cycles that battery is being used for. This way we can predict maintenance requirements. So in general, we provide our customers with a unique ability to proactively supervise its system. And in case of any issues, any failures, technicians know exactly that, for example, this light is not working and exactly why. So identification of troubles takes actually very limited amount of time, comparing, for example, to conventional system where if lights are not working, you require lots of time very often to identify the issue. From the economical perspective, solar system requires no civil works. Of course, again, relatively to conventional installation. There is no cables, no trenches, no substation required for the system to run, which means 30 to 50% lower investment, 10 times faster installation, and cheap and also very simple maintenance that is again supported by individual light monitoring. Now we are getting to the main topic of today's webinar, which is how to assess reliability of solar power supply. First of all, the question that we are often asked by consultants that you often ask us is, how can airport operate 365 days on solar? Well, the philosophy and the idea of solar system is following. As long as solar light can generate more power that it consumes, is going to work forever. When we analyze ability of system of 100 lights, 200 lights to operate 365 days, we always look at one single light, because the assumption is if single light, which is independently powered and charged, can operate for 365 days, an entire system will. So again, as long as light can generate more power that it consumes, it's going to work without interruptions. Now let's have a look at the consumption and generation. I think it's obvious for you that LED optics light consumes energy when the light is on, and solar panel that is a part of the fixture generates energy that goes into the light, that it is managed by the microprocessor and stored in built-in power bank. So energy generated by solar does not power the light itself. It recharges the battery, and the energy from the battery is powering the light. So those are basic principles. Now, what is the key driver of a power consumption? Let's speak about that. Power consumption is driven by airport operations, by amount of amount of flights that is processed by this particular airport. Let's have this. Let's see this example. When a particular airport has 12 flights per day, 12 flight operations per day, we estimate that a single operation requires 30 minutes of lighting. So in total, it is 6 hours of lighting that we need to process 12 flight operations per day. In order to power light for 6 hours a day during 24 hours cycle, we need 14 watt hours of energy. So this is not a consumption per hour, it's a consumption per day. So during 24-hour cycle, when out of 24 hours, light will be on for 6 hours, we require 14 watt hours of energy during this particular day. Then the next step that we take is we calculate how many actually watt hours we need for the months for this particular light to operate. In this case, it would be 14 watt hours times 30 days gives us 420 watt hours. That's the amount of energy that we need for the light to operate 6 hours per day, 7 days a week. A small remark, obviously we all understand that there is no airport that operates in this constant manner. There are sometimes peaks and there are sometimes decrease in operations. But for this exercise, we wanted to take an extreme assumption that airport operates 6 days a week. Every day the amount of operations is constant, and let's say it's on its peak. So we have just discussed power consumption. As I said, as long as power generation exceeds, so it is more than power consumption, the light will operate without interruptions. Now let's continue and let's discuss how we estimate power generation, because power consumption is easy. It is linked to airport operations. It is linked to energy consumption. So we can easily estimate it for the period of 1 year. Here, as you can see, we have estimated for a particular airport how much energy it would require to operate. Here is, we assume some seasonality of the operations, and we basically understand that this airport would need more or less 500 watts of energy on average per month to operate, to be able to operate 365 days and to service flight schedule of this airport. Now, let's speak about power generation. Now, power generation has its 3 key drivers. Number 1 key driver that defines ability of solar to produce power is it's called azimuth angle. Azimuth angle is orientation angle of PV module relative to the direction due to south. For example, azimuth angle of 0 would mean southwise orientation. Azimuth angle of -180 would mean northern orientation of the solar panel. Second driver of power generation is called solar panel power output, and in our case it can be 20 watts, 240 watts, or 600 watts. It all is linked to the size of the solar panel. And the third driver of power generation is called slope angle. Slope angle is this angle, so it's the angle of photovoltaic module from the horizontal plane. If we take a look at SP401 solar light, is a basic light that is used in S4GA installations, then our solar panel size is 20 watt, and angle, so this slope angle is exactly 33 degrees. It is fixed, it's non-adjustable. Now let's see how we can predict solar power energy generation in the specific location. First of all, we need to identify which location we would like to analyze. For this webinar, we have selected airport in Nigeria. It is called Sam Mbakwe International Airport in the city of Owerri. Airport looks like this here. It is cargo slash passenger airport, civilian airport. Looks like more or less like here. Simple airport, relatively small terminal, tower, 1 runway, 1 taxiway, 1 apron. That's actually an ideal airport that S4GA equips with solar lighting. Now, as soon as we know where we want to forecast this energy, we will go now to a special website that we are using. It's a great tool. It's called Photovoltaic Geographical Information System, and it will allow me to simulate monthly power output for selected location. So I hope that you all see right now the website. I have now transferred to the website that is called Photovoltaic Geographical Information System. It is actually available online to everybody. It is free of charge. You can select different languages. You can select different languages: English, French, Spanish, and Italian. And it's a great tool for solar systems for simulation, whether or not solar system can operate 365 days a year. If you want, I am going now to use chat, and I have just sent to everyone on the chat in Zoom website address for your future use. Now, what I'm going to do right now, I'm going to go to Owerri Airport, Nigeria. It's Owerri. You can see that here is Nigeria. Now I'm going to select the airport location. Yeah, this is the airport that we just discussed. One runway, let's say two taxiway, one apron. And I'm going to click here to read connected. And before I'm going to start doing anything, I'm going to click optimize slope and azimuth, because I need to know, first of all, what is the orientation of my solar system supposed to be towards regarding the south. So I'm talking about this orientation of solar panel. I need to know what is the optimal one, and the system tells me that the optimal one is 16 degrees, referring to south orientation. So I'm going to put it here, 16. Slope, as you remember, it's 33, because this is the slope angle for this one, for S4GA light. And we are going to put here in installed peak power. It is defined in kilowatts 002. 002 means 20 watts. Now we are going to click visualize results. So for this particular location, so for Owerri Airport, let's see what we have here. First of all, we see that yearly, annual energy production from a single 20-watt solar panel is 26,000 watt of energy. 26,000, so 26 kilowatt, 26 kilowatt hours of energy. And in January, we are going to produce 3,000 kilowatt hours. In June, 1.5 kilowatt hours. Why the difference? Well, obviously it's the seasonality factor. This is Nigerian winter. The first check that I can do here as a designer of lighting system, I can already, looking at this graph, see that if my system requires 500 watts hours of energy per month, then obviously, if I draw this line here, I can see that in all months of the year, from January to December, solar system from S4GA can produce more energy that it requires to consume to operate 365 days. If you remember the assumption was 6 hours per day, 30 days per month. For this, we needed 500 watt hours, or 0.5 kilowatt hours is the same of energy. That's the reason I have drawn this line here, because the graph here shows us photovoltaic energy output, kilowatt hours of energy. This is what we see in the blue columns. And by applying my line of how much energy I need to use, I can see that in most of the months, the energy, in all of the months, the energy that is produced is at least twice and sometimes 3 times, like here in July, the energy that is produced is 1.5 kilowatt hours. Energy required to be used is 0.5 kilowatt hours. So it's 3 times difference. We have 3 times more energy produced than we need to consume, which means, again, let me get back to my presentation. I have now activated my slide. I hope you all see that. So I am now at my presentation again. So now what we do as the next step, we compare energy that is produced with energy that is required to run the light. As long as energy required to be consumed in comparison to energy generated is lower, or again, energy generated is higher than energy consumed, solar system will operate 365 days a year on solar. During the next session, on the next part of the presentation, I'm going to calculate risk of blackout in solar runway lighting system, how we do that. But before I'm going to do that, I would like to stop for a moment and ask questions that you might be having. So now I'm going to switch to chat. And in case, now I'm looking at the chat window, and in case if you have any questions, please shoot. I will try to answer them. Do you have solar panel which can produce more than 20 watts if needed? The answer is, it is possible to do such system with a solar panel that has more than 20 watts. We can install 30 or 40 watts. That is correct. But I will show you later that for more locations that you can expect, and the 20-watt solar panel actually provides a sufficient amount of operating hours for the given airport. Another question, can S4GA be used in international airport? It is not mentioned in your product range. Yes, the S4GA can be used in international, regional, domestical, and civilian airports. It doesn't matter that the let's say, nationality or internationality of airport doesn't matter from the perspective of solar light. But of course, there are some details that needs to be discussed prior to installation of solar system in international airport. Why 33 degrees slope angle? Allow me just to maybe share with you the questions so you can see them all. Yeah, here. So why 33 degrees slope angle is fixed and not adjustable? We figure out that for, first of all, why it's fixed? Because in order for the light to withstand jet blast or heavy wind you need to fix the solar panel firmly to the light. Otherwise, it will be disintegrated with a jet blast. That's why the slope is fixed and the light has a certain redundant fixture. Existing LED lights inset can be integrated with S4GA systems. At some airports have centerline lights. Well, it can be integrated. That is correct. We can integrate power control of centerline with. We can control it from S4GA LCMS. What about inset lights to mark centerline? I don't understand the question, but if you ask me if inset lights can be powered with solar energy, I would say they can be, but financially it is not really feasible. So when we select airports where we install solar lights, we mostly focus on airports that have no centerline. I can tell you that even category 1 runway lighting system does not require obligatory inset centerline. So we focus on those kind of airports. If we consider 500 solar panel for installation in airport, what will be the efficiency and operating factor of it? I think this question does not really refer to the solar lighting anymore. But if you would like us to help you with this, I strongly recommend to contact us after the webinar, and I will be happy to assist. All right. I will continue my presentation. And I think that I will be able to answer more questions later. Okay, so the next question that I would like to discuss is how to calculate risk of blackout in solar runway lighting system. Why am I asking this question? Previously we have showed you that when monthly power generation is higher than monthly power consumption, the system will work without interruption. This is, I think it's pretty much self-explanatory. But the question that we shall ask as airports, as airport consultants and designers is, okay, but this is the monthly perspective. What about the daily perspective? What if during particular day of the month, we can experience a blackout? What if when we see at the month perspective, everything looks good and everything looks as if system can operate during the whole month? But what if we have at the beginning of the month a lot of energy generated, then we have cloudy weather for 2 weeks, and then at the end of the month we have again 1 week of very sunny weather? What is the risk that we will experience and how to calculate the risk that we can experience blackout during a particular day or days? I think this is very important question to be also understood. So how do we and can we, as S4GA, can we forecast and can we assess a risk of blackout during specific days? For example, what really we are asking about and what really you normally are interested is, well, if we look at the light battery level, yeah, on this graph you can see, hold on, on this graph you can see axis where you have battery level from 0% to 100%. On this axis, we see months of the year from January 2022 to December 2022. Now, these small columns represent daily battery level of the light. As you can see here from this graph, the battery during the whole year never drops below 60%. And even if I wouldn't understand solar lighting, I would be able to say, well, that's all right, because as long as battery in the light is full every day and it never drops to zero, the light will operate without interruption, which means and defined by us as 365 days scenario. So in this scenario, a light will be able to operate 365 days. So as long as it will operate 365 days a year without interruption, if battery level in solar light never drops to zero. How does blackout looks like and how it might look like? Well, the same graph, but let's imagine a situation when, as I said, beginning of the months, we have a very sunny weather, then couple weeks of bad weather. And when we say blackout, what we really mean is that the battery level in any given light drops to zero, which means light stops its operations, it's inoperative, and airport doesn't have the light. So it's called blackout scenario. Is there a way to predict if we are going or not going to experience this blackout scenario for the particular light? Well, there is, and I'm going to show you how we do that. First of all, we need to go back to photovoltaic geographical information system, to the same website I just used. We again will have to select a location, identify optimal azimuth for the solar panel. Then we have to define daily consumption. And as I said before, daily consumption is actually linked to airport operation. So to define daily consumption, what we as an S4GA or you as a consultant and designer, what you have to do, you have to ask the airport a question. Well, how many hours of lights you need in the worst case scenario, meaning in the longest day of the year? And I'm of course talking about continuous operations. Do you need 2 hours per day to operate? Do you need 12 hours or 24 hours? This is critical to understand the daily consumption prior to calculating of the blackout, risk of blackout. And then we are going to go to special place in this simulation tool that is called battery performance. And if percentage of days with the empty battery is 0%, then solar system will operate 365 days. If it's not, then we will experience blackout. Let's talk about how to perform this 365 days battery level forecast. First of all, again, we need to understand a few basic things. Solar panel, as you know already, it has a 20-watt solar panel. The slope angle is 33 degrees, and battery capacity is 216 watt hours. Why and how we know that? Sorry, how we calculate this? We have 2 batteries. Each battery has 9 ampere hours of energy, 12 volts. So 2 times 9 times 12 give us 216 watt hours. Based on S4GA measurements calculations, we know exactly what would be the daily energy consumption for SP401. Now we are going to calculate it for Runway edge light. This is the light that consumes the most energy out of all S4GA portfolio. So for Runway edge light to operate, for example, 6 hours per day and to be on so-called standby for 18 hours a day, we need 14 watt hours of energy. To operate 12 hours a day, 25. To operate 24 hours non-stop every day, daily power consumption is 45 watt hours. 45 watt hours. This is what we need to operate this light for 20. When I say operate the light, I mean we activate the light and keep it on. This is what I mean to operate the light. So when light is on for 18 hours, we need 35 watt-hours of energy. When light is on for 24 hours, we need 45 watt-hours of energy. So now I'm going to move to photovoltaic geographical information system again. And let's, for the same airport, which is the Owerri airport in Nigeria, let's go to the tab in this website that is called Offgrid. So Offgrid tab, if we see its definition, this is a part of the simulator that calculates performance of solar system that is not connected to electricity grid, but instead rely on battery storage to supply energy when the sun is not shining. This is exactly solar light. So in solar light, we rely on battery storage. So we use battery energy stored in the battery to power the light. And we supply energy with solar to supply energy when the sun is not shining. But we use a photovoltaic system to provide this energy to the battery. Now, this system, what it does, it actually calculates daily variation in electricity consumption for the system to simulate the flow of energy to the users and into and out of the battery. So this is an exactly simulator tool that will forecast for us battery level in 365 days cycle. What do we need to do that? First of all, installed peak power. Installed peak power is for solar light, SP401 solar light is 20 watt. Battery capacity in watt-hours is 216. That's what I already explained. Discharge cutoff limit is, especially for lead acid batteries that degrade quickly, if they allow to completely discharge too often, they will degrade quickly. But this is why we have a cutoff that is normally imposed, so that the battery charge cannot go below a certain percentage of full charge. This should be entered here. And the default value is 40%. In S4GA lights, we have 30%. This is driven and this is managed by microcontroller in the light. So when the battery will reach 30%, light microcontroller will cut off the energy from the light. Consumption per day. As I said, this is absolutely critical parameter that we need to take and understand, because it defines whether or not the system will operate 365 days. Let's get back for a moment here. Let's assume that airport in Owerri in Nigeria needs to operate lights to keep them on for 12 hours every day, 7 days a week. Therefore, we need 25 watt-hours of energy, and we are going to put them here. Slope is 33 degrees, and azimuth is 16, as we have discovered before. Now we are going to visualize result. As you can see here, when you look at simulation outputs, the percentage days with empty battery is 0. The percentage days with full battery is 1997. So you can see that whenever from January to December, every month you have green columns. Green columns indicate that actually certain percentage of days the battery will be full. A red column, if it would appear here, it would indicate that the battery, the amount of days with empty battery. Just to give you a perspective. Let's try to use the same system operating for 12 hours a day in Iceland. Now I have selected Iceland. Since I'm doing that, I need to recalculate my optimal slope for Iceland. It's minus 2. I'm going to go back to Offgrid. Select -2 azimuth, because for Iceland it's slightly different than for Nigeria. And I will recalculate results. And what you suddenly see is that the system in Iceland cannot operate 365 days a year, every month. But interestingly, from April till September, system has only the battery forecast only has green columns, which means that it actually can operate 1, 2, 3, 6 months out of the year in Iceland. The system will operate 12 hours a day. But from October, November, December, January, and February, and also March, this particular system cannot operate 12 hours a day. But what if the one can say, all right, yes, so solar system is not for Iceland. And then we would strongly disagree, because if we get back to this daily energy consumption, and we see that 6 hours a day requires 14 watts, let's see that what if we decrease this energy consumption to 14 watts a day? Will it change anything for Iceland? Suddenly, we have only 4 months of blackout for this light. If we go to 6 watts a day, for example, what happens? 6 watts, it represents more or less 2 hours of energy. With 6 watts, we have 2 months when system will not work. So again, yes, the system, even with 2 hours a day cycle, will not operate in Iceland. But the thing is that for some airports, I'm talking about some regional airport or maybe some smaller municipal airports in Iceland, this can be absolutely acceptable, because they might not even operate during December and January due to, well, bad weather conditions. Specifically, I'm talking about airports without instrument landing system, without precision approach. Those airports, there are many of those, and they do not require 12 hours a day operations. They might be absolutely okay with 4 hours, 5 or 6 hours of day. And when such airport would approach us from Iceland and would ask us, can we operate solar system? What we will tell them is, look, the solar system in your airport can operate 2 hours a day, February, March, and November. And I will change my consumption to 14 watts, which is 6 hours a day. But if you need to increase operations, then from April till October, you can operate more hours. So again, we will forecast for them that we have certain hours, certain months, so where you can operate only 2 hours. This would be November, January, and February. And for the rest of the year, you can easily operate up to 6 hours a day. So in this case, if airport accepts this cycle, then we can say that yes, then the solar system is for you. But if they tell us, no, look, we need to operate, we operate in heavy traffic, we are commercial airport, we require 24 hours or 12 hours of lighting per day, then we say, no, this is not a system for you. So we are very clear with airport about whether or not solar system can operate or not. Getting back to our presentation. Now, we have made some simulation prior to this webinar, and look what situation looks like. Actually, in many places, as I said, in many places of the world, such as Brazil, or Nigeria, or South Africa, or Indonesia, or Saudi Arabia, our SP401 light with 20-watt solar panel that has a 33-degree slope. Our system can actually operate 24 hours a day in Indonesia, in Saudi Arabia, in South Africa. In Nigeria, maximum is 18 hours. In Scotland, the system can operate from November to February 2 hours a day, and from March to October for 10 hours a day. Again, as long as airport accepts this limitation, we guarantee 365 days operation with this cycle. Because what matters in solar system feasibility study is we call it solar autonomy. So how many hours per day we can guarantee operation of the system. Just to show you this example of Jizan Regional Airport. Again, we go to Jizan Regional Airport in Saudi Arabia. Let's see. No, this is not the one. Yeah. So we are in Saudi Arabia in the particular airport. We need to again see optimal slope, which is -4. We go off grid. We already have all our parameters in. So we calculate -4 here. Sorry, we input -4 to azimuth that we just calculated. This is optimal azimuth or optimal orientation. And now we are going to use 45 watts hours of energy, which means 24 hours for this location, and see what happens. As you can see, if we set up S4GA light in this regional airport and we activate it and never switch it off for 365 days a year, the light will continue to operate without interruption. So again, what it means without interruption, they are going to see, if they would measure battery level, they are going to see something like this rather than that. Now, the last item on today's menu is we are going to speak a little bit about differences between S4GA and our competitors. The goal of this particular part is not to badmouth anybody, it's just to show you why S4GA claim, and that is what we guarantee, 365 days a year operations. Why we say we're the world's safest, why we install our system permanently in the airports. So again, are all solar lights equal? Just to remind, SP401 light has 20-watt solar panel output, 33-degree solar tilt, and entire solar panel is facing one direction. Our competitor company is called Avlight, has solar panel with a solar tilt of 90 degrees. So when I say 90 degrees, here we have a right angle between solar panel. This is a solar panel. Yeah. So the angle between solar panel and horizontal plane is 90 degrees. They do have 20-watt solar panel that is divided into 4 pieces and installed into the 4 walls. Design, in my opinion, looks quite appealing because, well, you have solar panels that are built into the walls, so you don't need to. You can just simply take the light, move it to another location, and where as a temporary solution, I think it's pretty good. But the question is that needs to be always asked: will it be able to operate 365 days in a particular airport? So let's see. We know that for the typical airport, for the typical engineer, the main difference between these 2 lights is actually the design. They are both solar. They look more or less, but they look different. From the perspective of solar supply design, the greatest difference is in the angle. So we have 33 degrees, they have 90. So let's see how changing of a slope in Saudi Arabia would change battery forecast for the year. So I'm going to change my slope from 33 degrees to 90 and visualize results. What you can see is that during the months of May, June, July, and August, so 4 months out of 12, the system that with S4GA solar design were operative 24 hours a day without interruption. When we put solar panel vertically, it suddenly became non-operative. So in May, the system, 72% of days, the system will have empty battery. The same is in August. The system will work 50% of days in September. So this only tells you that you have to be careful when you plan solar lighting system. You might ask, okay, what if the system needs to be active only for, let's see, 12 hours a day and not 24, because not airport requires 24. Let's see if we have it on for 12 hours a day. So we only need 25 watt of energy. We are going to change 45 to 25 and recalculate. In this case, in Saudi Arabia, there are 2 months when the system is barely operational. And of course, you have to remember that this system, when the battery is new, the capacity is 100%. But when the system becomes older, the capacity shrinks. So what if the capacity of the battery that is new, has 216 watts, would shrink to, I don't know, 180? What would happen? Still okay. 150. Still okay. So for this particular location, the system will be able to supply 12 hours of operations. Now, what if we go to, let's say, Congo and do the same? In Congo, because it's closer to equator, 90-degree angle creates much more bigger difference between 33 degree and 90 degrees. So in Congo, even 12 hours a day of operations will not provide. If the solar panel angle is 90 degree, the same light will not be able to provide sufficient amount of energy. So you will experience blackouts. If we change, one thing I didn't do, I didn't check my slope angle, sorry. Let's see. It's the same. It's the same, -4, okay. So I'm gonna change now to 33 degrees and recalculate. I have just did this and we'll recalculate. Again, in Congo, 33-degree angle of S4GA light will be able to support 12 hours a day. Will it be able to support 18 hours a day, 35 watts? Let's see. It is. If we go to 90 degrees again, angle, you can see that with this cycle, so 18 hours a day, 3 months you have of the year, you have green columns, rest is green, red or red, green. So system is not valid for 365 days of operations. So again, I'm saying that you have to be careful when doing a feasibility study. You have to consider, first of all, slope, solar panel size, battery capacity, and again, consumption per day. Consumption per day is defined by in discussion with the airport. And it's the critical parameter here, because we can, as I said, we can use our system here in England. It will not work for 18 hours a day. Let me just show you, 33 degrees. It will not work. But if I decrease capacity to, I don't know, 8 watts per day, then in this location from March to November, the system will work perfectly. So all is the matter and perspective of consumption. And consumption is linked to amount of operations that we want to process. So now it's the time for questions. Thank you very much for watching this webinar. I'm sorry it took slightly more time than I expected. I hope that I managed to explain some basics. If you have questions, please ask them. As far as I know, we have today people from 15 countries, from non-sunny to sunny, and I think it would be very good to get different points of view on this topic. At any given time, only one battery is used. The second battery is backup. Am I right? Yes, that is correct. At any given time, only one battery is used. There are 2 batteries in the system. One is primary source of power. The second one is backup. But the idea is that both batteries can be a backup to both batteries. So it doesn't matter which one would fail. The second one will continue to power the light. Thus, S4GA can integrate an existing airport with inset and elevated LED lights in full from conventional to solar, if asked for a recently installed lights. If yes, then can you share any case study? We do have this capability of combining solar and conventional. However, this topic requires more explanation. Abrar, I will be happy to do that on the separate call with you, if you don't mind. Any more questions? All right. I believe that if you don't have more questions, then it feels to me that either maybe I was so clear about it, and then I'm happy. In case, of course, if you do have more questions to me personally about this, or you would like us to help you to do feasibility study for the particular airport of your interest for your project, please don't hesitate to contact me on my email. Again, I'm Dmytro Kuczeruk, and the email is here above. I'm here to help you. So thank you all very much for the time that you have invested in today's webinar. I'm very grateful for you being here, and I really truly hope that from now on you can have more confidence in applying solar systems for your projects, and that you know how to approach a feasibility study of solar system. In case, again, if you need our support, we are here for you. We can do that with you. Thank you. Thank you very much. Bye-bye.